This is the outline of chapter 24. So we will introduce a new variable called electric potential. And then we will also introduce something called equipotential surfaces, which is related to the electric field lines we introduced before. Okay, and then we'll also introduce how to calculate the potential for different structure, like potential due to charged particle, due to electric dipole, due to continuous distribution. Okay, something similar to what we did before. But here, the electric potential is also a field, but it is only a scalar field, so it makes things easier to calculate than the electric field. Because the electric field is a vector field, the vector field has amplitude and also direction. So to calculate the E field will be more difficult. Okay, in this case, we introduce another variable called electric potential, which is related to the E field. Yeah, actually, at the very, at the end of the chapter, there will be an elegant equation to relate the electric potential and the E field. Okay, so here we will try to calculate the potential, and then we will also calculate the field from the potential. Yeah, so actually this part. So the idea is to directly calculate the E field may be difficult. So we will try to calculate the easier variable first, which means the electric potential. And then by some calculation, by some easier calculation, then we can get the E field from the potential. Okay, so next I will introduce electric potential energy of a system of the charged particles, and then the potential of the charged isolated conductor. Okay, so here we'll introduce electric potential. So it says the electric potential V, so we usually denote it as V. Okay, at the point in the electric field of a charged object is given by this definition. Okay, this is a definition. This is a definition. So it means that it is like, okay, so where W infinity is the work that would be done by the electric force on a positive test charge Q0, where it brought from infinite distance to P, which means that originally this test charge, this is a test charge, we place it at infinitely far away. Okay, so we will also define the potential. The potential energy there is U equals 0. U equals 0. If you place it to something nearby a E field, of course, we assume that this bar will generate the E field something like this. The E field something like this. Okay, so there's an E field. Okay, and if you need to place this test charge to here, you need to have some force, because this is a positive charge, this is a positive charge. So they have repelling force according to the Coulomb's law. So if you need to put this charge to there, then you need to do some work. So this is the work done from here to there to here. Okay, so this is W infinity, and then over Q0. Q0 is the charge amount of this test charge, Q0, and then take the negative sign, and then it will be the negative. W infinity will be negative U. U is the potential energy. Okay. We have not defined what is potential energy yet. We are actually defining electric potential. This is electric potential energy. Okay, they are different things. So where it brought from and infinite. Okay, so and U is the electric potential energy, that would then be stored in the test charge object system. Okay, so stored in this system. Okay, so if a particle with charge q is placed at the point where blah blah blah, so we will have another equation. So this may be more useful for us, at least in this course. So actually it is like V equals, so yeah, so it is just like you move this thing over. So you have the potential energy stored in the system equals to the charge multiplied by the electric potential. So this will be a useful equation. Okay, and then we have some more formulas on this page. So it says so change in electric potential is like originally we write it as U equals Q times V, but actually usually when we consider the potential or potential energy, we will consider the potential difference rather than the absolute value. So just now I mentioned that we define U equals 0 at infinitely far away. Actually, this is not very important, but if we really define U equals 0 at infinity far away, then the equation for the general U will be more elegant. Of course, you can just define it to be like U equals let's say 10 joule. Joule is a SI unit for the energy. This is okay, but usually when we consider the potential difference between this point and that point, if you add 10 joule to here, then you also add 10 joule to there, and then you consider difference, 10 joule and 10 joule will just cancel it out. So usually we'll just try to make things easy. And here is the point that if we have, for example, if we have a point, the initial point and the final point. Okay, so this point may have a electric potential Vi, and then this point may have another potential Vf. If you have a test charge here, Q0, if you move it from here to there, then the delta U, of course you need to do some work to do so. So the delta U, the potential difference, will be Q times Vf minus Vi. Okay, or maybe I just make it Q. Make it Q. So Q matches this Q. Okay, so similarly, if we consider the work done, so the work done will be negative delta U. So we just plug this one to here. So we have a negative sign. And then here we also consider the conservation of energy, 能量守恒. Okay, 能量守恒. So in mechanical cars, this might not be true because there might be some frictional force to consume the energy. So for some situation in the let's say the physics 1 cars, conservation energy might not be true. Usually you use the conservation of momentum, 动量守恒. But here, when we consider the electromagnetic force, so we usually will ignore the energy loss. So usually conservation of energy is okay. So in that case, we will consider to have a conservation energy, which means, for example, if a system have an initial condition, it should have something like the initial kinetic energy. K means the kinetic energy, and then U means the initial U means the potential energy. So the total energy should be like Ki plus Ku is the total initial energy, and then for the final stage, it should have Kf plus Uf. Okay, so this is the final kinetic energy and the final potential energy. As much as we assume the energy is conserved or conservation of energy, then these two variables should be equal to each other. And then we try to move over, for example, if we try to move this term over and move this term over, so we will have delta k will be kf minus ki. So this is the kinetic energy change. So delta k equals delta f minus delta I, and also delta u equals uf minus ui. Okay, so if we try to collect those terms, you can see that delta k equals is actually equals to a negative delta u, and delta u is actually this one, q delta v. So we have negative q delta v equals this thing. Okay, so this one is due to the conservation of energy, and then we may also apply, so for this one, we don't apply any work to the system, so we assume the energy is conserved. If we have to do some work on this system, then we need to add a term W apply there, which means that you apply some work so that the total energy change. The total final energy should have changed. So it will be like a negative W apply, and then you move the term over. So you have a negative delta U plus W apply, something like this. Okay, so so this is some simple equation. Okay, so here let's take a look at a sample problem. Okay, so it says electrons are continuously being knocked out of air molecules in the atmosphere by cosmic ray particle coming from the space. Okay, so 他说就是电子就是一直就会被一些宇宙射线去被打中了，就是然后那些电子就会被打中之后就会被赶出那个空气的分子。Okay, so continuously knocked out by the molecule in the atmosphere by the cosmic ray particle coming from the space. Okay, 所以21章的时候就提过，就是在那个EM wave 的频谱里面呢，最高频的就是那些什么 gamma ray X ray 那些 ，OK， 就是指这个 cosmic ray 就是指那些 ，OK。Once released, each electron experience an electrostatic force F due to the electric field E that is produced in the atmosphere by charged particle already on Earth. Okay, so it says there will be a E field. There will be an E field generated by charged particle on the Earth. Okay, near Earth's surface, the electric field has the magnitude E equals 150 nano per coulomb, and is directed downward. Okay, what is the change delta U in the electric potential energy of a released electron when the electrostatic force causes it to move vertically upward through a distance d equals this value? Through what potential change does the electron move? So there at least potential change, and also what is the change delta U. Okay, so it asks you at least two things. Okay, so here you can see it asks you the electron is knocked out by the molecule, so we have an electron there, and then we also have the E field. So in the E field, okay, this is a negative charge, so the force should be pointing upward. Okay, so this force will make the electron moving upward. Okay, so we assume that D is 520 meter. Okay, so actually like this. Okay, so here we will have the work done. Work done is a scalar. Okay, but it is like a dot product, which is F dot D. F dot D. F is the force acting on this electron, and D is the displacement vector. Displacement vector. 位移向量. Okay, so you can see F and D points to the same direction. So this should give you a positive value, and it will be like Q times E dot D. Here, okay, so we make this variable change. So F is Q times E, or E, or negative. Actually, this one is negative E rather than E, so be careful about that. So this is a negative charge. So we have a negative E. So you can see E and D points to opposite direction. So E dot D gives you a negative value, and then multiply this negative value, still a positive value. Okay, so here we have it will be like a negative E times D, and then cosine of, okay, E and D points to opposite direction, so cosine of 180 degree. Okay, so this one will give you -1. I'll cancel with the negative sign in the front. Okay, so here E will be 1.6 times 10 to minus 19, and then times E is here 150, and then times D is 520 meter. Okay, so all the variable are SI units. So yeah, it's okay. So the final value is 1.2 times 10 to minus 14 joule. Okay, joule. Okay, so this is actually not the answer. So I just erase the box. Okay, so actually it asks you the change delta U. So delta U should be negative W, which would be negative 1.2 times 10 to minus 14 joule. Okay. Okay, so actually the potential energy reduced. It is just like, okay, so the electron is actually follow the force, or follow the E field, yeah, to move there. So it is like a spontaneous procedure. So the potential energy, I mean the electric potential reduce, and so as the the electric potential energy reduce, and so as the electric potential. So finally, it asks you the potential change, which means the electric potential change delta V should be delta U over Q. Okay, so it's like negative 1.2 times 10 to negative 14 over, this is negative 1.6 times 10 to minus 19. So this is 4.5 times 10 to the fourth power. Okay, the SI unit here is volt. Okay. Okay, this is also the answer. This is also an answer. So we need to answer these two things. Okay, or if we use scientific prefix, it will be 45 kilovolt. 45000伏。Okay, so one thing I would like to emphasize is that, okay, for this one we call it electric potential. Sometimes we will call it voltage. And the SI unit of voltage is volt. In short form, it is V. So the variable is V, the SI unit is also V. But this V is the voltage, 电压, and then the SI unit is volt. Okay, so I have heard many students, yeah, even in ECE say free voltage. Oh, that's not correct. They are mentioning V volt at that situation. So you need to distinguish voltage and volts are different. Volt is of course a name of the physician, So this is the SI unit, and voltage means, yes, somehow similar to the electric potential. Yeah. And of course, this is the energy. So the SI unit will be joule. Joule. Okay, so this is pretty easy. Okay, so next we will introduce something called equipotential surface. Equipotential surface. In Chinese, this is called 等电位面. Okay, so and the E field. So actually, this thing is related to the electric field lines. Okay, so here it says adjacent point that have the same electric potential from an equipotential surface, which can be either an imaginary surface or a real physical surface. So it can be imaginary surface, somehow similar to the Gaussian surface. It doesn't necessarily to be here. So for example, let's say here may be an equipotential surface. So it doesn't necessarily to be a practical surface or physical surface. But sometimes there may be a physical surface to make it equipotential. Yeah, especially if it is a conductor. So then if you don't apply too much strength things to it, then usually it is a equipotential surface. Okay, so here it says family of equipotential surface associated with E field due to some distribution charge. Okay, so here you can see a graph here. There are 1, 2, 3, 4 surface, equipotential surface. So we denote it as a V1, V2, V3, V4. So 4 different equipotential surface. So the work done by the electric field on a charged particle as the particle moves from one end to another of path 1 and 2 is 0. Okay, so let's see. Path 1 is here. Okay, so this point is on V1. This point is also on V1. So they are on the same equipotential surface. So which means that if the charge move from here to there, then the work done will be 0, because it is like work done will be negative delta U equals negative Q times Vf minus Vi. So in this case, for the path 1, Vf and Vi are also V1. So it is like negative Q V1 minus V1, which is 0. So like this. Okay, so, and also for path 2 is here. Actually, you can see that this path does not lies on the surface V3. So it goes out a bit and then come back to the V3. But actually, when we consider for path 2, okay, so W also equal this thing. So it is a negative Q V. So it is still, the final point is V3, the initial point is V3, so it is V3 minus V3, which is also 0. So in this case, you don't really consider how it goes. It only related to the starting point and the end point. Okay, you just subtract the electric potential and then multiply by Q and then take a negative sign will be the work done. So for path 1 and path 2, both of them are 0. And then for path 3, this is actually here. So this is not 0 anymore. So W will be negative Q. And then Vf. So from here to there. So this is F, this is I. This is final, this is initial. So this is V2 minus V1. V2 minus V1. And then for path 4. Okay, so this is not directly go from V1 to V2. It goes over V2 and then come back, but still end in V2. So actually it's still for path 4, W equals negative Q q v2 minus v1. So it makes a w, let's say this is 1, this is 2, this is 3, this is 4. So w3 equals w4. Okay, so it's here it says, so because each of these paths begins and ends on the same equal potential surface, and thus there is no net charge in potential. And then here it says the work done as the charged particle move from one end to another of path 3 and path 4 is not 0, but has the same value. Okay, they are not 0 and has the same value for both of these paths. Yeah, because both of the initial and final potential are identical for the two paths. Okay, so this is an easy demonstration. Okay, so here, I can also slightly mention that actually the equal potential surface is of course a surface. It will be something like the E field. The E field line will be so you can see, you can actually see that this is an E field line. This is also another E field line. Let's say E field line. So the E field line will be perpendicular to the equal potential surface. Okay, so the E field line, I mean the E field line, always perpendicular 永远都跟那个 equal potential surface 是垂直的 equal potential perpendicular to the equal potential surfaces okay. Yeah. Okay, so here, so in the previous page, it only shows the equal potential surface and the E field in a visual way. So here we try to use some mathematics to describe all these things. So here it says the electric potential difference is actually like a delta V, Vf minus Vi will be a so-called a line integral. Here is called a line integral. Okay, so different from the previous case. For the Gauss law, we have a surface integral. Surface integral is like E dot dA. Okay, if it is a closed surface, we draw a circle. If it is not, then we just leave it like this. Okay, so E dot dA. So also for line integral, if it is a closed contour, then we can also draw a circle, something like E dot dl, something like that. But for this case, if the starting point and the end point to be the same thing, then delta V will be 0. So for this case, we don't consider F and I to be the same point. So we don't draw a circle here. Actually, in chapter 29, when we talk about the Ampere's law, we will have the circle there. So that thing will be like an integration of a B dot ds will be mu 0 I enclosed, something like that. But you will learn it in chapter 29 later on. Okay, so here let's come back. So here, just want to mention that this is line integral. Okay, so we use S to stand for a vector along a line, and then dA means the area. So they are a bit different. For the mathematics textbook, usually it will write it as a true integral sign to specify it is a surface integral or this is a line integral or single variable integral. Okay, so Yeah, this is a bit different. Yeah, this is actually an integral in 1D, but a bit different from what you learn in the calculus class. In the calculus class, you usually have something like integration of fx dx, and then integrate. If it is a definite integral, it should have a lower and upper bound, something like this. Okay, so you actually integrating something also. For example, this is fx, so you integrate from a to b, will be something like this. Okay, and this is the x-axis, so you try to cut it along this way. But here we can have an initial point and final point, and then we will have a path connecting the initial point and the final point. So it's just like initially the charge is placed here, and then we try to move it to the final point along a specific path. So along this path, we can always define the ds. The ds is of course a tangent line. So ds will be the tangent. The direction is the same as the tangent line at that point. Okay, of course the tangent line will be like in two directional, but of course as much as you have the direction from I to F, you can clearly see that which is the correct direction you should choose. For example, the direction should be from top left to bottom right. So you can see that ds should be point to the bottom right rather than top left. Okay. Yeah. So here we can see this is a line integral along this line rather than the x-axis. So for the x-axis we don't have this dot product, but here for the line integral we have a dot product. This is a vector. This is also another vector. Okay. So we need to come up with the dot product. So which means that for this path, we can do the things like we just separate into many parts. Okay, many parts. For each part can be regarded as a straight line, although the whole line is a curved line. But as much as we cut it into many small elements, every small element can be regarded as a straight line. Then yeah. And for every point, it should have a e vector. Okay, e vector. For example, sorry, this is not e vector. This should be the vector of ds. Okay, it should have a ds there. And for this point, e field should be somehow pointing to this way. Okay, something pointing this way. And for this point, okay, ds point to this side, and then e field point to that side. If you point to that side, and then for example for this point, ds point to this side, and then this is e field. This is e field. Okay, why I can draw the e field line like this? I mean the e vector like this. So it somehow follow the e field line. So these are the e field line. So yeah, this point is somehow line between. So you can see the e field line should point to this direction, and then for this point, ds point to that side, and then yeah, actually this point is actually crossing the e field line, so e field should point to this side. Okay, somehow similar to this. And after we try to cut it into a small element, and then we can also distinguish for every element what is e and what is ds. Then we will be able to calculate e dot ds for every element, and then we try to add them together. And this will be the line integral, which is also somehow similar to the Riemann sum. Yeah, actually, it's actually a Riemann sum, I should say. Okay, so this is a Riemann sum. You will be able to calculate it. Of course, in mathematical class, when you learn how to calculate a line integral, then the function may be much more complicated. But usually in physics class, then yeah, usually the calculation will be more easy. Okay, so here you can see this is a line integral, and then take the negative sign will be the potential difference. So this is how we related the electric potential and the E field. And actually the line integral of the E field. Okay. Okay, so here we try to just simplify it as V equals Vf minus Vi. Okay, V is just like the delta V, or sometimes we can just choose Vi to be 0 because only the relative value is important. I mean, only the potential difference is important. The absolute value is not very important. So usually we only consider the potential difference. So yeah, or similar, you can just choose a Vi to be an arbitrary value. If you want to make it easy, just try to make it like Vi to be 0, then Vf will be V, or V equals Vf minus Vi. It's still okay. It just depends on how you see it. Okay, so here it's just like V equals negative integration of I f e dot ds. So this is an important important relationship between the electric potential and the E field. And of course, in high school physics, I think you should have learned this before, but not the integral form. So in high school physics, you should have seen this expression. Okay, so the condition is like in a uniform field of magnitude E, the change in potential from a higher equipotential surface to a lower one, separated by distance delta x, is delta V equals E times delta x. So for that case, it will be like if you have these 2 points, they have delta x, and then for example E is pointing to the right side. So the delta V between them will be like negative E times delta x, something like this. And if E is not pointing to the right side, or for another case, if E is pointing to that side, then you should consider the projection. Okay, then EY shouldn't contribute to the delta V. Only this part, only the EX will contribute to that. So it should be something like EX delta X if E is not points to the same direction. If you just denote it as negative E delta X, then you just keep in mind that E and delta X should be points to the same direction. Or E is the x-axis component. Okay, so this is what you should have learned in high school physics, and this is the more general form. Here we consider E might not be uniform, or might be or with a strange pattern. Okay. So here we also mention another SI unit for the E field. So in chapter 22, we already know that E should have a SI unit to be Newton per Coulomb. From E equals F over Q. Okay, from this one we can get this, because the SI unit for F is Newton, for the SI unit for Q is C. So E should have a SI unit of a Newton per Coulomb. Here, as much as we have this is the potential, so this should have a SI unit of V, volt, and delta X should have a SI unit of a meter. So if we just move this one over, so we should have V over M to be the SI unit of E. So both of them are correct. So in the quiz or exam, you can either choose one. But I would say SI unit is really, really important. Okay, so try to write the correct SI unit for the answer. Okay, every SI unit will count for 1 point. Okay, yeah, so let's see. Yeah, so let's finish off this sample problem before we have a 10 minutes break. Okay, so here it says 2 points I and F in a uniform electric field E. The points lie on the same electric field line and are separated by distance d. Find the potential difference Vf minus Vi by moving a positive net charge from Q0 from I to F along the path shown, which is parallel to the field direction. Okay, so we are required to calculate this as okay Vf minus Vi. Okay, yeah. So here we can see the E field is pointing downward, and also the path is also going from top to down. So this is I, this is F, so it moves along here. Okay, so this is a straight line. So along the whole line, ds should be pointing downward all the way. Okay, so here we can calculate Vf minus Vi to be negative integration of E dot ds. E dot ds. So this is the definition. Okay, so we can see as much as E is pointing downward and ds is also pointing downward all the way. So in that case, it is just like negative integration of E times ds times cosine of 0 degree. Cosine of 0 degree. And as much as this is uniform, so we can just move it out. So it turns out to be integration negative E times integration of ds. Okay, which means this is nothing but the length of the path. So this is d. So this is negative E times d. Okay, nothing special. So this is pretty straightforward. Okay, so next we try to do something strange. So now find the potential difference Vf minus Vi by moving the positive net charge Q0 from I to F along the path ICF. So I, C, and F. So this is perpendicular to the E field line and then go from here to there. So this is D. This is This is also D. This is also D because this is a So this is a right angle triangle. Okay. So this is a right angle triangle. This is 45 degrees. So this is D. This is also D. Okay, so if you have paid attention, you should know that the delta L, the delta V, which is a which is Vf minus Vi, shouldn't relate to the path. So we should have come up with the same answer. But this sample problem is just to show you, we try to do this and then verify that it will give you the same result. Okay, so let's see. So here, we try to calculate this path first. So which means this is a Vc minus Vi will be negative integration of E I to C E dot ds. E dot ds. Okay, here we can see that. So this is I, this is C. So ds is pointing to the right side all the way, and then E is pointing downward. So it will be like integration of I, C, and then E times ds cosine of 90 degrees. So this thing is 0. Okay, this is 0. Okay, so yeah, this is, so the integration will also be 0. Okay, I forgot the minus sign here. Okay, so this is Vc minus Vi, and then next we should consider Vf minus Vc. So later on, when we just add them together, then Vc and negative Vc will cancel. So finally we come up with Vf minus Vi. Okay, so here, considering a negative integration of a E dot ds from C to F. Okay, so here is like negative integration of CF and then E ds cosine of 45 degree. Okay, so this is 45 degrees. So the angle between E field and the D vector is actually this angle. So this is 45 degree. Although this one and this one are also 45 degree. But when you consider the dot product, this is the E field direction. This is the ds. So we should consider this angle. Okay, so this is 45 degree. And then E is also a constant. So it is like negative E integration of C to F ds cosine of 45 degree is 1 over square root of 2. 1 over square root of 2. Okay, so this is the line of this, the length from C to F. Okay, so this is D, this is D. So according to the Pythagorean theorem, this is square root of 2D. Okay, square root of 2D. So this is negative E and then times square root of 2D and then times 1 over square root of 2. Okay, so this square root of 2 and square root of 2 cancel. So finally, we come up with negative ED. Okay, then we just add them together. Then we can have VC and negative VC cancel each other. We have VF minus VI to be 0 plus negative ED will be negative ED. So we get the same result as before. Okay, so yeah.